All right, so we have first problem is projectile motion, and we're looking at a projectile that is fired from the edge of a 150-meter cliff. So the height of the cliff is 150 meters at an angle of 30 degrees with the horizontal. No air resistance. Thank you. We're asked to find the horizontal distance from the gun to the point where the projectile strikes the ground, and then the greatest elevation above the ground that is reached by the projectile, right? So the way to go about the problem is that we have to consider the vertical and the horizontal motion separately. Then we apply our equations in the y direction. We apply the equations in the x direction. We'll figure out the time t for the projectile to hit the ground, because we know that it has to go down by a height of 150 meters like that, and we'll use that to find the horizontal distance. And the thing to remember is, what is the condition when you have maximum elevation?
Velocity or acceleration is zero.
Velocity. Your velocity in the y direction,
Velocity is zero.
in
Yes.
the y direction is going to equal 0, right? So that is the condition for your maximum height. All right. So what you're given in the problem is that you have your initial velocity, which is 180 meters per second, and your original position is at 150 meters, and you know that the acceleration is in the negative direction, right? So if our coordinate frames are in the x and y axis, so this will be minus 9.81 meters per second squared, right? And your acceleration in your x direction is what?
Zero.
Zero, right?
Zero.
And the easiest thing to do is to always define your coordinate system right at that origin, like that, right? So then you know that it has to travel down by a distance of 150 meters, like that, right? Okay, so next, let's look at vertical motion, right? Right, so for the vertical motion, right, you have your, we have our 180 meters per second, right? Angle theta, right? So you have a component in the x and you'll have a component in the y, like that, right? So you'll have v y naught like that. And then you have a negative acceleration, which is equal to minus 9.81 meters per second squared, right? And we can straight away say that the initial component for the velocity, so Vy naught, is just equal to our 180 meters per second times sine of the angle theta, which is equal to 30 degrees, right? So sine of 30 degrees. So sine 30 is 1/2, right? Am I remembering that correctly? Yep, it is. And that equals to 90 meters per second, like that, right? And then from our derivations in class, we knew that our velocity in the y direction at any time t is equal to the initial velocity in the y direction plus my acceleration times the time t, right? But we know that the acceleration is negative. We know the initial velocity here, so we know that Vy is equal to 90 minus 9.81 t, like that. So let's call this expression number 1. Integrate this again to get your position, which is, again, we don't need to integrate it. We've already derived it in class, right? So that's just Vy naught t plus half at squared. So that's just equal to 90t minus 9.81 t squared divided by 2. So we can just simplify that to 4.90 t squared, like that. Good stuff. All right. Okay, and then for your horizontal motion, right, we know that Vx naught is just going to equal 180 meters per second times cosine of 30 degrees. And that is equal to, can someone tell me?
I got 155.88.
All right, so if we go with 155.9, that's good, right? All right, let's go with that. And we know that your position vector x is equal to Vx naught times t, and that is just equal to this 155.9 times t, right? So let's say 3 like that. So now putting our coordinate point there, right? We know that the projectile strikes the ground when y is equal to minus 150 meters, right? So it goes down, putting our frame of reference over here, it goes down 150 meters, so minus 150 meters like that, right? So if we substitute that into our expression, right, so we get minus 150, so that's in expression 2. So in 2, it's equal to 90t minus 4.90 t squared. Can you guys solve quadratic equations in your calculator real quick? Anyways, are you guys able to do it? I don't have my Mathematica handy today.
I forget how to do that in calculators.
All right, so say we get t is equal to 19.91 seconds, like that, right? And then if we substitute the t into equation 4, sorry, no, equation 3, so you get that your x is equal to 155.9 times 19.91, and you get that x is equal to approximately 3,100 meters. So that's one answer.
And is that the position at which the ball lands?
Yes, that is the position at which the ball lands, right? Because we know at the position at which the ball lands, it has to go down by 150 meters, right? So we basically found out the time it would take for it to go down by that much. And then we plugged in that time into this position equation over here. And that's how you got the position at the time t, right? So this is your position. That's what the question asked you, right? The horizontal distance where the projectile strikes the ground. So this is part A over here. All right. Another thing which we hadn't written in class, which will make our lives a little bit easier, would be this expression over here. That if I take time out of the expression, right? So Vy, so my y velocity at any time squared is equal to my initial y velocity squared plus 2ay, like that, right? So let's call this expression number 4, because with this one, then we don't need to, because otherwise you have to go find out what the time is going to be, and then you have to plug that in. But here you can directly just find out the position when Vy is equal to 0, right? So that's just a shortcut for you guys. So yeah, so writing that expression out. So at max height, Vy is equal to 0. So if I write this equation out, all right, let's write it out. So we have Vy squared is equal to V naught Y, which was how much? 90, right? So 90 squared minus 2 times 9.81 y, right? And now we're just trying to find out the point at which Vy is equal to 0, right? So when Vy is equal to 0, y is max. And from above, if you solve it, y is equal to divided by 2.981, like that, and it'll end up being in meters, right? So anyone solve that real quick for me?
$412.8 meters.
So let's say 413 meters, right? But that, your question asks you the greatest height above the ground, right? So you have to account for this height because your coordinate frame is at this point, right? So the max height this way is 413 meters. So you've got to add this as well. So remember to do that. Your max height above ground is equal to 150 plus 413, so which is equal to 563 meters. And that's your part B. All right.
Professor,
Yes.
oftentimes whenever we have projectile motion questions, they often ask for the greatest elevation above ground height or something like that.
Mhm.
So the equation you just gave us, will it work for all? Will it work all the time that they ask us for?
Yes, it will. When you this expression is good for all projectile motion on Earth. Absolutely. Yeah.
Oh, I see.
We derived
And-
it last. We had derived it last week on Thursday too. It's just I didn't write it out for you guys today. But yeah. Any more questions? All right. I'll meet you guys again. Okay. Yeah, so that expression will be true for whenever you're trying to find the max height, right? It's just Vy equals 0. So
If you had to do the other way, you were speaking about having to find time and all that. How would it go?
So in order to do that the other way, right, I would have to use this expression over here, find out the time at which t equals, Vy equals 0. Then I find out the time at which t equals 0, at which Vy equals 0 from this expression here, and then plug that into this expression. So it's basically an extra step to find out what the y would be, right?
Oh, I see. Yeah.
Yeah. So this expression just takes time out of the equation and you get your answer in one step. But the other
Right, I
way,
can see it.
you do Vy equals 0, 90 minus 9.81, so 90 divided by 9.81 will give you your time. And then you plug that into this expression here to get what your y would be. So yeah. All right. Good question. Any more questions, guys? No? All right. Last question. Wow, we're almost out of time. Okay. So we've got an automobile A, which is traveling east at a constant speed of 36 kilometers per hour. And you have an automobile A, which is, as automobile A is crossing the intersection, you have an automobile B, which starts from rest 35 meters above the intersection and moves south with a constant acceleration of 1.2 meters per second squared. So you're asked to find the position, velocity, and acceleration of B relative to A 5 seconds after A crosses the intersection. So after A has traveled 5 seconds to the right, you're asked to find the position, velocity, and acceleration of B relative to A after that, right? So in order to do this problem, it's good to define your coordinate system like this over here, where this is the point where the intersection happens, right? And then you have B moving in the Y direction and you have A moving in the X direction, right? So basically these axes are defined in the direction of the road, right? And what we're told is, we are told that VA is equal to 36 kilometers per hour. And we're told that this is constant, right? So we're told that the acceleration of A is equal to 0, right? And it starts from this origin over here. So we know that the position is also equal to 0. And then in the problem, we're told that the initial velocity of B is equal to 0, and that the acceleration of B is in the downward direction, right? So, you know, the magnitude is equal to 1.2 meters per second square, but the direction is downward. So we'll just keep the sign negative over here, and this is constant. And we know that the initial position of B is equal to 35 meters. Right? So let's just do all our unit conversion so that we're working with meters per second, right? So the velocity of A, doing the conversion is, you have 36 kilometers per hour, then 1 kilometer is equal to 1,000 meters, which is 1 kilometer, and then 1 hour is equal to 3,600 seconds, right? So you have hour cancels, cancel, so that 36,100. So you're left with 10 meters per second for this one, right? So for A, we have uniform motion, right? There's no acceleration. So for A, you can straight away write that your XA, and it starts from the origin, right? So going back to our expressions, it was just XA0 like this plus VAT, right? But this is equal to 0. So this is just going to equal 10t meters, right? So let's say that this is expression 1. So at t equals 5 seconds, right, we have the acceleration of A is equal to 0, right? The velocity of A is equal to 10 meters per second. But I want to write this as a vector because we're looking at motions in different directions, right? So I know that VA is equal to 10 meters per second horizontally in the X direction. As a vector, what do I write it as?
10 meters per second in the x-axis or I
I
component.
hat direction, all right?
Right.
So let's use using I hat and J hat and unit vectors makes life really easy. All right, so VA is equal to 10 I hat in that direction, right? And then the position vector XA is equal to, we know that it moves in 5 seconds, 10 times 5. So this comes out to be 50 meters. So your position vector, right? And again, now we're writing the position vector generally in both IJ. So let's use R, right? So R is equal to 50 I hat, right? It's moved 50 in the I hat direction like that. So now we've figured out what's happening with A. Now let's go and look at what's happening with B. All right, so now moving on to B, I know my B is, I have a downward acceleration, right? So if I write my, guys, we're going to go slightly over time. I apologize, but just want to finish this problem, if that's all right with you guys. Don't hate me. So we have velocity of B is equal to your initial velocity of B, which we know it starts from 0, plus AT, like that, right? And we know that it's 1.2 negative, so we can just say that this velocity B is equal to 0 minus 1.2 T in that direction, right? And then similarly, we know that the position B, again, it's just in the Y direction. So that's going to equal your initial position plus your velocity, initial velocity times T, plus your acceleration, half acceleration times T squared, right? So we know that the initial position is 35. VB naught is equal to 0. So that term is just equal to 0. And then AB, it's going downwards, right? So it's going to be minus half times 1.2 times T squared, like that, right? So now if we define things at times T equals 5 seconds, we know that we know the acceleration, we're good there. The velocity, or the magnitude of the velocity rather, to be complete about it, is just minus 1.2 meters per second squared times 5 seconds. So this comes out to be minus 6 meters per second. And then the position B, we're just subbing things into the above expression, right? So 35 minus half times 1.2 times 5 squared, like that. You get that that is equal to plus 20 meters, right? So now when I write these out as vectors, see that my acceleration of B is 1.2 in the negative j hat direction, right? So 1.2 minus 1.2 j hat meters per second squared. See that my velocity B is 6 meters per second minus. We know, but the minus means that it's downward, so it's 6 minus 6 j hat meters per second, like that. And then my position vector for B is plus 20. So it's still 20 in the j hat direction, right? And now when you want to find out your relative positions, right? So the question asks the position vector of B relative to A, right? So now we know that R of B, and that's why working in vectors is so easy. But when you look at the solutions online, you'll see that you can do it in both ways. But I really prefer to do it in vectors because it just makes life easy. So R of B relative to A is just equal to RB minus RA. So that's just 20 J hat minus, what was RA? 50 I hat, right? So minus 50 I hat meters. Velocity of B relative to A is just equal to VB minus VA. So that's minus 6 J hat minus, what was VA? 10 I hat minus 10 I hat meters per second, right? And then similarly, you have the acceleration of B relative to A, which is the acceleration of B minus acceleration of A. Acceleration of A is 0, and acceleration of B is minus 1.2 J hat meters per second squared. So you found all of the relative terms that you wanted to find, and your answer is described. Now, you know, the questions might ask you to start finding angles and things like that, but I'm pretty sure that you guys can do that, right? You have I hat and j hat directions, and then you can find the relative angles to fully describe your solutions as well. All right, any questions with this one? No? Easy peasy? All right, homework 2 has been posted. It's due next week. Homework 1 is due today. So there's a bunch of you that haven't submitted it. Please make sure that you get that in. All right, do you guys have any questions for me?
Nope.
Thank you, Professor.
All right, thanks, guys.